they will close the classroom after 6 next Thursday.
Oh.
So we might have a hard time getting in. We found an operator for video customer, but they usually close down the classroom after 6. So
that's Dave?
Yeah.
Yeah, just ask to see if we can do something.
Is that nice? Yeah.
All right, good afternoon. So let's see a couple of things. Review session. First of all, let's talk about that. I plan it for Thursday even-ish. The problem really is I was hoping to do it 6 till 7:30, but there's last class somebody was asking, hey, can we webcast it and all this kind of good stuff. The problem is they typically close this room around 6 o'clock. There's some, flexibility. But would it be okay if we have it at 5 o'clock, 5 till 6:30? Would that be a major problem? It makes it a little bit easier for the people scheduling it and so on and so forth. So is that okay? So, no? Well, it's going to be webcasted. That's the good news about it. And if you have any questions, you can always send in questions in written advance. So if you have any particular question you want to be addressed, send me an email or something like that. I always can do that. So let's do it 5 o'clock on Thursday. Okay? Good. Let's see what else. I'm waiting for the final word on the room for the midterm. I've asked it in beginning of end of August, and they would get back to me. So I haven't gotten back. But well, I'll let you know. It's definitely will be on the website and so on and so forth. So next week is going to be fairly lightweight otherwise. There's no lab, no new homework. Basically, let's prepare for the midterm. Yes? there's still, that's right, thank you, Mike. There's still one lab for those of you who basically had a good time on last Monday. Obviously, we have to pick that one up. So there's one lab on. For those of you, the Monday lab is still going to be on this Monday. But then we're going to resync again after that. The next lab after that is going to start again on Monday. Okay. Let's see. Homework number, what is it? Number 4 is going to be due the week after. So I give you some extra. I don't want to make sure it's due at the same time as the midterm, so it's going to be due the week after. And let's see what else is there. There was one more thing that I had in mind. Oh yeah, I think you already should be aware of the fact that the midterm is going to cover lecture 1 till 8. 8 is last lecture, and we stop at the end of propagation delay. So power is not included in the midterm. There's going to be 3 questions. One of them is going to be more, well, you can expect it. One is going to be more like on device things, and the second one is going to be more like on DC characteristics, steady state, and there's going to be one more towards propagation delay, transient analysis. So it's kind of the 3 questions that you may expect. Let's see, anything else? That's, project. I think the week after that, yeah, probably the week after that, I'm going to shuffle the lectures around a little bit. Because if I follow the normal sequence of lectures, we would first talk about technology scaling, then about wires, and then we would go to logic, and before we could start the project, it would take a long time. So what we're going to do after the midterm, I'm going to start actually jump-starting a little bit, and we're going to do a couple of lectures on logic, complex logic first, and then we're going to talk a little bit about arithmetic, because that's going to be important. I really would like to get the project started as soon as possible, and you need to have some background material before you can get into that. So I'm going to reshuffle the lectures a little bit, but that's not going to impact things in a big way. It's just the way we order things. Just to give you an idea what the project's going to be all about, it's going to be a multi-phase project. The first thing is going to be just kind of, you do some, we'll give you most of the stuff, and what you do is analyze. And then we say, okay, now that's, you know how to do that now. So you should get better now, right? We should be able to take the same design and do a lot better in some aspects. You might make it extremely cheap, or you might make it very small, or you might make it very low power, or something like that. So what we're going to do is, we just thought about it this morning, it's going to be a little, tiny little filter, digital filter we're going to build. Sounds very complex, but it's not much. So something that does some low-pass filtering or something like that nature. It's going to be mostly arithmetic, so there's going to be no sequential logic in there. It's going to be a combinational logic block that we're going to build. And as I said, we're first going to start with an almost given design. We're going to give you the cells, and you're going to have to do all the analysis and put it together. And then you say, okay, now all hell breaks loose. You can do whatever you want to, but make it good. So that's the idea, and that's how we're going to progress through the semester. Okay? Well, let's see. Anything else on that? No. Any questions? Anything unclear about midterms? Homeworks. One last thing. Assignment 1 and 2 have been graded. I don't think they're there yet, but the place to pick them up is in 253 Corey Hall, where we also depose the extra handouts. It's on the desk of Rosemary. If you go 253 Corey, there's this big room where there's a number of people, cubicles. You go towards the back of the room, and there's one desk there where actually always the assignments are sitting, and the homeworks will be sitting there as well. Okay, so you can start picking them up probably next Monday or so. Okay, alrighty, that's done. So what we're going to do today is talk a little bit more about power, and that's still analysis. So far we haven't done very much yet in terms of design, right? I showed you circuits and I told you how to analyze them. Slowly but surely now we're going to do some design. Say, well, you have to optimize it for something. How do you minimize delay? How do you minimize power? That's kind of the fun part, right? Everybody can run spice runs, right? You have enough 1,000 monkeys, somebody's going to get it right eventually. Now, the fun part about design is to have a problem at hand, and you have a set of targets, and then you start messing around with your transistors, schematics, and so on and so forth to make something that meets your ultimate goal. And that's where we're going to start going on today. Actually, we're going to do one particular topic, which is very important. It's simplistic, but it's something that is going to come back over and over again. It's buffer sizing. And it will become a lot clearer what I mean by that while we're going through this lecture here. But it's an important topic because you will see whenever you do digital design, sizing of buffers is going to be something that's coming back over and over and over again. Okay, good. So let's recapture a little bit the last lecture. Last lecture we discussed propagation delay. Remember 2 techniques. Technique number 1, use a current source, estimate the capacitance, and you have that TP is equal to CL VDD over 2 times the average current that I'm going to be using to discharge that capacitor. So you have a current source discharging a cap over a value of VDD over 2. The other approach is the resistive approach. You say, well, I'm going to replace my transistor with an equivalent resistor, which is linear, and has approximately the same effect as the nonlinear resistor in terms of propagation delay. So in this case, we get TP is 0.69 times R equivalent times C, CL. And we spent a lot of time last lecture on figuring out how that capacitors looked like, what all the different contributions to that capacitor were. There's one other thing I mentioned last lecture is that the propagation delay, this is the propagation delay assuming that you have a step input function, that the input to the gate goes from 0 to VDD in 0 time. Okay? In reality, that's not the case. In reality, the input to the gate will typically be a slope. And that's going to delay your gate a little bit. It's going to make it a little bit slower. Very complex analysis. As I said, don't bother. It's a lot of paper, a lot of equations, pages and pages. Actually, this equation works quite well. It says actually the delay of a gate. I showed you that dependency. It shows actually that there's almost a linear dependency between the input slope and the propagation delay. Right? It's not completely linear, but it looks linear enough. So something that people very often use is says, well, gee, the propagation delay of a gate with a certain ramp input, not a step input, is equal to the delay with a step input. We know that. We can compute that. Let's just apply a step. You get the delay. Plus a factor eta. I express it here as a ratio of 2 voltages, but that doesn't really matter. Assume that you have a parameter eta, which is maybe 1/2, 1/3 approximately, times the propagation delay of the gate in front of it. So if I want to get the propagation delay for this gate as a function of a ramp, of the ramp input, so what I'm going to do in this case is say, well, the propagation delay is going to be equal to the propagation delay of this gate when I apply a step to it, plus eta times the propagation delay of the preceding gate. Because the propagation delay of the preceding gate is kind of a measure of the slope that you will see at the input of that particular gate. Okay? So that's a very simple equation that works quite nicely. How to compute eta? Don't worry about it. Typically what you do is simulate it. You match it. You basically do some simulations. You say, well, it's approximately linear. What's the slope? That's my value of eta. You do an empirical type of analysis. And that works quite nicely. So then you can do fun things. Like, for instance, like in this case here. Suppose I have 4 gates in a row. And I want to figure out what the propagation delay of each of those individual elements is going to be. So the first one is directly driven by a step. So that's easy. The propagation delay of gate number 1 is equal to TP step. You apply a step input and you find out what the propagation delay is. Obviously, given the load, I assume that all those inverters are equal size. So you have to take into the load factor of inverter number 2. The propagation delay of number 2, here you can see that the input is not going to be a step anymore, but it's going to be a slope because it's the output of a previous inverter. Well, there we can use our simple equation. It's Tp is going to be Tp step plus eta times Tp step. And you can keep on repeating that. Because if we now look at the third gate, what would it be? Well, it's going to be equal to Tp step plus eta times the propagation delay of the previous gate, which we have here. So it's times Tp step plus eta times Tp step, and so on and so forth. And you see you get a recursive equation. You keep on adding recursion to it. And you can do the same thing for 4, and so on and so forth. So you can actually easily compute the impact of the slope on this whole chain. And what you would expect, and that's normal, right? You go to a chain of inverters. The first one will have a very nice slope, right? You have a step. Second one is going to be like this. The third one is going to be a bit like that. And you can see that the slope will degrade over time. You can get around that by sizing up your gates a little bit. That's what we often going to do, is if you have a chain like that, you're not going to keep them all the same. You might actually size it up a little bit. Or there's some other tricks. There's some circuits out there which we will talk about way later. Let's say about 6-7 weeks from now. Some circuits that allow you to take a bad slope and turn it to a good slope. A circuit that takes in something that kind of is slowish, you feed it in there, and out of this comes a very nice, crisp waveform. It's called the Schmidt trigger. But don't worry too much about that. So there's ways for us to clean out slopes and make them nice again. Okay? But you can imagine that if you keep on going 2 different chains, that your slope will deteriorate if you don't do anything very careful about it. Okay? All right. Let's see, what else do I want to recap over last class? This is kind of the whole discussion of capacitors in one slide. It kind of summarizes it all, and I think it's a fairly good summary in the sense that it takes all the effects into account. Remember, if you look at load capacitance of a gate, it comes from it's partially due to what we call the intrinsic capacitance, which is a capacitance which is provided by the driving gate itself, and the load capacitance, which is the capacitance which is contributed by the fan-out, all the connecting gates. Okay? Now, as you can imagine, connecting gates provide mostly what? Gate capacitance. Well, you look at and you have a bunch of gates following you, and what you see is the gate capacitance of those transistors. You don't see the diffusion caps. While the intrinsic capacitance, that's at the output, that's at the drain of your transistors, that's going to be drain to bulk capacitance, junction capacitance. Okay? So we can see here, like say you have a particular inverter. That's the guy here. We make the PMOS 2 times as wide as the NMOS, which obviously is going to provide more capacitance. That's unfortunate because we want to make them the same strength. You have to make the PMOS double size. Typically also means that the PMOS will contribute more capacitance than the NMOS does. It's kind of slowing down our overall design, which is something we don't like, but what can you do about it? Well, there's certain things you can do about it. We'll talk about that later. So both of them provide a drain to bulk capacitance, dBn, dBp, and assume that the junction capacitance are approximately equal per unit area. You can imagine that the PMOS will provide 2 times more junction capacitance than the NMOS device. We also have this gate to drain capacitance. Remember that little coupling capacitance between the input and the output, which is as we explained last class also, the only thing we really have to worry about is the overlap capacitance. Because when you apply a step, this thing here, the PMOS is the devices are either in off mode or in saturation mode. And in both modes, there is no gate capacitance between gate and drain. There's only overlap capacitance. All the other capacitance is either to source or to the bulk, and we don't worry about those. Those don't count for the output. So, so you have to double that because of the Miller effect, right? This thing goes up, this guy goes down, Miller effect, we double the capacitance. Okay? So that's the intrinsic capacitance. And then the load capacitance is nothing else than all the gate capacitance we see of the connecting transistors. We have a PMOS, we have an NMOS. PMOS twice as large. Assume that the oxide thickness is about the same, right, which it always is. Every process, PMOS and NMOS, have exactly the same oxide thickness. So they have the same capacitance per unit area. So what we see here is that the PMOS, again, is going to provide 2 times more gate capacitance than the NMOS does. So the total capacitance is basically diffusion capacitance times 3 times W, where 3 times W is the capacitance per unit width. And the gate capacitance, which is 3 times W, times the F factor, the fan-out factor, is, if we make the transistors bigger with the factor F, you obviously have to multiply this with a factor F. Okay? Fan out of 4 factor. And this is all driven by resistance R on divided by W. The wider you make your transistor, the smaller, basically, your resistance is going to become. Okay? And that's basically it. And then you plug it into your equation. You have your equation for your R on. You have your capacitive numbers. And bingo, out comes your delay. Okay? So that's kind of in a summary, this whole lengthy discussion about capacitance that I did last time around. But this, if you remember this already, you're in the right direction. Okay? Let's see. So let's talk a little bit about power. Dynamic power dissipation. Here you have to take all capacitance into account. So dynamic power dissipation is charging and discharging capacitors. So if we first have this inverter here, which has a load capacitance of some fan out, we have intrinsic drain or drain capacitance, we have our gate capacitance here at the input. If this thing flips up and down, if this goes from 0 to high, this is going to go from high to 0, you will see that all the capacitance will basically go to a 0 to VDD or a VDD to 0 transversal. So in order to compute the dynamic power dissipation, you have to add all the capacitance together and multiply this then by, so you get C total times VDD times the swing, which is typically also equal to VDD, so it's VDD squared, times the clock frequency, times alpha 0 to 1. Remember the alpha to 0 to 1, that's the probability that I will have a 0 to 1 transition at a clock edge. And that's not always the case. It's a switching probability of our gate. Okay? Not every gate will switch at every clock cycle. It's only one circuit, part of our circuit, that does that all the time. It's the clock network itself. Obviously, the clock network on the chip, which is this very complex thing that takes a clock and distributes it to the whole thing, that's going down, up and down every clock cycle. So you can imagine that a clock on a chip consumes a lot of power, and it does. Take a good old microprocessor, one of those multiple gigahertz microprocessors, and you figure out where the power goes. It's fair to state that about 30 to 40% of the power goes in just the clock itself, just distributed at a very high frequency signal all over the chip with all the capacitance that hangs off it, because that goes up and down at gigahertz rates. While, let's say, your multipliers or your adders, not all nodes go up and down all the time, so your activity is much lower there. Okay? So that's kind of where we were. So let's go a little bit forward and talk about some other sources of power dissipation in digital circuitry. At the end of last class, I mentioned the word short circuit current. And the short circuit current is quite straightforward in the sense that if I have a gate like this one here, and I have a slope at the input, right? I don't have a ramp. You will see that from the time that my voltage goes beyond the threshold of the NMOS transistors. So initially, we're at 0, means the PMOS is on, the NMOS is off, right? That's the initial condition. And then I start rising. Once I reach the threshold of the NMOS device, the NMOS will start to turn on. But the PMOS will still be on at the same time as well. So during that period of time, both NMOS and PMOS will be on simultaneously. And there will be current flowing through the whole chain. We will have current flowing from VDD to ground. Now, how long will this last? Well, till the PMOS turns off. When will the PMOS turn off? When the voltage reaches VDD minus the threshold of the PMOS device. Once you basically get within 1 PMOS threshold of the supply voltage, the PMOS turns off and the short circuit current will be finished. Now, short circuit current is useless. It doesn't do any good. It just consumes power. Because it doesn't help us for basically making things faster, it doesn't make it better, it doesn't do any good for us at all. So obviously, a good goal in life would be to reduce the short circuit current as much as possible. So the question is how to do that. If you're not careful, actually 20% of your power could go to waste just like that. If you do basically, and people were not very careful in the past. If you look at the late 80s, early 90s, people didn't care. And they were throwing all this kind of power through the door because they didn't worry about it. And then people start worrying about it, and they come up with some solutions. Making it absolutely zero is going to be very hard. You can, but it's not worth the effort. If I can keep it below 5%, I'm OK with it. I say, OK, that's fine. I'll live with it. There's a couple of ways of doing this. Let's think about this. What would be one way of making sure that you never have short circuit current? What would that be?
The threshold voltage of the NMOS is greater than PV minus threshold voltage of the.
That's right. That's exactly right. If I would reduce my supply voltage below, so that's below VTN plus VTP. So let's say I have a threshold of half a volt or something like that for PMOS and NMOS. If I reduce my supply voltage below 1 volt, it's impossible for both transistors to be on at the same time. You're never going to have subthreshold current. So that's one trick. Very low supply voltage operation. The problem, obviously, your circuit is also going to be very slow when you do so. So it's a performance factor. But it's something that is something to think about. If you want to do very low power logic, that's actually something to consider. What else could we do? Think about it, right? The longer I'm going to be in that little transition zone, the worse I'm going to be off. Right? Yes?
Can we change our gate capacitance, lower our gate capacitance with the change of the oxide thickness?
Yeah, well, basically, make sure that your input slope is fast. Right? If I go to the transition zone really fast, obviously there's going to be less time for me to have short circuit current. But you have to be careful with that, because if you don't do it well, you might end up with some problem. But indeed, making your input very fast compared to the output seems like a good idea. And let me show you an example of where this can work really well. Suppose I take my inverter here and I put a load capacitance on this thing, which is really, really, really big, like infinity. Right? I make a huge capacitance and I put it at the output. And then I put my input and I make it go through a certain slope. What do you think that the short circuit current is going to be? Actually, it's going to go to 0. Why is that? Well, if I make my input, if my output capacitance is really, 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 really big, let's say make it infinity, the output will always stay at VDD. It only is going to go very slowly downwards. Right? You're going to have a very slow slope at the output. You have fast slope at the input, very slow slope at the output. Now, if you think about it, so this thing goes quite quickly to VDD, or somewhere in the intermediate region. So I turn on, initially, it's only the PMOS on. I turn on the NMOS. But if, 1 second here, if this is at VDD, what you can see is that if this is at VDD and this is at VDD, there's no voltage over this PMOS device. So no current will flow basically through it at all. And as a result of that, I will have 0 short circuit current. Right? I would like to have only the NMOS on, obviously, right? That's what you want to do. You want to discharge. I turn on the NMOS, bingo, pull it down. And I want to make sure that the PMOS turns off as fast as possible. But unfortunately, it's not off immediately. But if I keep the voltage over that PMOS very small, there will be no current flowing through it. And there will be no short circuit current. So very slow input, very fast input, very slow output basically gives you very small short circuit current. And that's actually shown in this chart here, which plots the short circuit current as a function of time. And you see here for different capacitance value, 20 femtofarad, 100 femtofarad, 500 femtofarad. And you can see that the short circuit current goes down with the size of the load capacitance. Now suppose I would do the reverse. Suppose I'm now going to make my output capacitance really tiny. I make it 0, let's say. So a single electron comes by and bingo, my output goes from VDD to ground. Bingo. Just one electron is enough because there's no capacitance. That's the worst case condition, because now you can see that the PMOS is going to have a full VDD range over it while it's still on. So you have your NMOS is on, your PMOS on, but your PMOS will have the full VDD range over it. So we're going to have maximized current through the PMOS, maximized short circuit current. So, interesting conclusion, right? Make your load capacitance as big as possible. Now, that sounds like, yeah, good idea, but kind of dumb as well, right? Think about it. I want to make a good circuit. I want to make it low power. And what I'm going to do is I'm going to put a huge capacitance down, which is going to increase my dynamic power and make my circuit infinitely slow. So from a practical perspective, this is not something I really would like to go after. So we have a problem here. Right? You cannot go for solution 2. That's really bad. Solution 1 is very attractive, but it's not perfect either because it's really slow and high dynamic power. So what we're going to do is put some water in the wine, just a little bit. And say, well, what would happen if we ensure that the input and the output slopes of our gate are approximately the same? If we size our transistors in such a way that we always have approximately equal slopes at inputs and outputs. Turns out, if you do that, that your short circuit current is going to be 5 to 10% max. So it's not ideal. It's not the best possible solution, but it gets close enough. It basically makes sure that yeah, we have a fairly small amount of time in the transition zone, and we make sure that the PMOS doesn't get into this hard turn-on mode for a long period of time while we're discharging. So this is not a new result. It's a result that was published already in 1986, a famous paper by Harry Vendrick, where he analyzes these things very carefully, and he came out with exactly that same conclusion. Do some slope engineering. So a good designer will make sure that you have a complex network. You're going to look at all the slopes of your signals, and you want to make sure that they're approximately in the same order. They can vary a little bit, but keep it in the same order of magnitude approximately, and you're going to be fine from a short circuit. All right, that's that. So we're not going to worry too much about this. We assume that you're going to do that. Right? Now, if I see designs where you see some really fast signals and then some really slow ones, I'm going to get worried. I say, well, maybe you can do something better in terms of sizing of transistors and so on and so forth. Okay. Last factor, an important factor of, actually the most important one that basically starts to emerge these days of power dissipation is leakage. Leakage is what it says. It's kind of charge dribbling away. Charge that's stored on a capacitor or on a node is going to dribble away to ground or to VDD. Now, in the good old days, the only thing we had to worry about was the fact that we had diode leakage. Remember that every transistor, like we have a NMOS, this is a PMOS transistor here. You have a PMOS transistor, you have a N substrate or a well, and a P plus drain or source region. Reverse bias diode, I think you remember that, diodes, you've seen diodes before. If you look at the current equation of a diode, it looks like this, right? This is approximately 0.5, 0.6 volt. If you forward bias the diode, it turns on and a lot of current flows through. If you reverse bias, you basically block the diode. Does that mean there's no current flowing to the diode? No. There's actually still some reverse currents flowing to the diode at a point in time. So all those junctions we have, all those source to bulk, drain to bulk junctions, reverse bias junctions are going to leak. There's going to be some reverse current flowing through it all the time. Okay? Especially if it's, for let's say, if this would be sitting at let's say, this is at VDD and this is at 0, we have a full VDD over the junction, we'll have a current which is sitting in approximately right here. The good news is that it's small. It's orders of picoamps. Small currents. So not too much to worry about. It's not something that the only place we really used to worry about them was in DRAMs. We'll come back to that later. DRAMs obviously are relying on the fact that you store charge on a capacitor, and the longer the charge stays on that capacitor, the better. So if this capacitor, this charge kind of leaks away, you're going to have to refresh that DRAM memory. So it's going to cost you time and effort and so on and so forth. So that's why we were worrying about junction leakage most of the time. So it's, you have to be aware it's there, but it's not the key thing that I'm worried about today. However, there's one thing that you should be aware of is that for those of you who might end up with a company working for automotive stuff or something like that, if ever you go to a company that does things for airplanes or for engine control, those things run to run not at room temperature, but maybe at 150 degrees Celsius or something like that. A lot higher temperatures. Actually, the junction leakage goes up substantially with temperature. It actually doubles every 9 degrees Celsius. So if I go from room temperature 30 degrees Celsius to, well, that's not room temperature, 20 degrees Celsius to something like 120, 110, that's 90. That makes it easier. 90, that's a factor 10. So you have 2 to the 10 times more leakage in those conditions. So high temperature electronics are a lot more sensitive to those junction leakage effects. But as I said, that's, again, it's not the most dominant factor for most of the other designs. Yes, it does. Yes, it does. It really goes up very, very, very sharply. Yeah, if you look at the dependency, you can actually put the two dependencies together, and you will see actually that junction leakage actually gets a larger fraction when you go up in temperature. Okay, so here's the real important thing. Here's the thing we really should worry about, and where people are worried about more and more. It's transistor leakage. I remember what we discussed way back. It says, first lecture or second lecture. A transistor is a switch, and either have an on resistance, and when it's off, it's infinite resistance. And then I said, well, that's not true. Transistors don't do that. Actually, it turns out that when a transistor is off, when the VGS is equal to 0, or where your VGS is below the threshold, we still have some current flowing through the device. It's a very different mechanism. It's not anymore the transport of charge as we see, majority charge basically from the source to the drain, as we saw. It's a very different mechanism that happens. But we have current flowing through from the drain to the source. So as a result of that, for instance, I take my inverter, and I put VDD at the input, NMOS is on, I assume that the PMOS is off. In reality, there's still going to be a leakage current flowing to that PMOS. On the order of nanoamps. So it's a couple of orders of magnitude larger than what your junction leakage would basically be at. The same thing is true in the reverse condition. When I put 0 here, PMOS is on, and the NMOS is leaking. And again, we have direct current flowing from VDD to ground, static power dissipation. And that becomes important. If each of those basically leaks a couple of nanoamps, and you have thousands and millions and billions of gates, You add all those things together, and suddenly you add something that drains the batteries of your cell phone without doing anything, which you don't like. Obviously, I would like to basically have standby power. If I don't do anything, I would like to have a circuit consume nothing. Right? That's the ideal concept that you have to go after. So this has become a big problem. It's something that popped up around the 130 nanometer technology node, became bigger and bigger in 90 nanometers. In 60 nanometers, the 65 nanometers, they say, well, gee, the leakage is really a problem. So what they did is they didn't scale the gate oxide as fast anymore. They did some other things, tricks that basically allow them to control leakage better. They kept the thresholds larger too. And at 45 nanometers now, the Intel, IBM, and things like that finally said, we're going to have to change the way we design the transistor to a certain extent to make sure that leakage stays within control. So there's now technology type of things that basically try to deal with this. But let me explain a little bit what's going on here. So this is similar to the plots you did in the homework. Remember your second homework, your second homework. Second homework, we asked you to plot this ID versus VGS curves, right? And typically, you plot those on a linear curve, and you get something like this, right? ID versus VGS, and you get something like this. But if you put it on a log curve, when you take the log of the current, and you have VGS and linear scale here, you get a different perspective. So let's say that suppose our threshold sits around right here. Here the transistor, depending on VDS, is 1.2 volts, so our velocity is saturated. So this is in saturated regime. Transistor is saturated. Once we, however, go below the threshold, you would expect that you would hope that the current goes to 0 immediately. That's what you would like to see. In reality, if I look at this log plot, I don't see that at all. Actually, we see a linear type of decline of our current. And even worse, when VGS is equal to 0, the current is not equal to 0 at all. There's still some current flowing. Now, why is that current there? Well, let's look again at our transistor a bit. Who of you has ever heard about a bipolar transistor? Do we still teach bipolar transistors occasionally? A little bit? Where do we do that? In 130? 140? 140 does bipolars. I don't think 105 does bipolars anymore, right? A little bit? BJTs? 8 weeks? Oh well. That's not when I taught it. Okay. So think about it. What is a BJT? It's NPN, right? Or PNP. It's a stack of semiconductor layers with different type of doping levels. Now, take my transistor. An NMOS device is NP, N plus, P, N plus. Does that sound familiar? Looks like a NPN device. There's a bipolar transistor there. However, with a normal bipolar transistor, we have a contact. This is called the base. We don't call it the channel or anything like that. That's the base. In a bipolar transistor, the base connects directly. You have a direct contact, and you inject current into that base. In our case here, this base is capacitively isolated from the gate collector. But if you think about it, this is kind of like a bipolar transistor. You have your gate here, so you have your source and your drain. You have your channel, NPN. And you have a capacitive coupling from the gate into that channel, and then another capacitor which couples the substrate capacitance, basically your depletion capacitance. Right? So we see that actually the gate voltage couples kind of like a capacitive divider into the channel. So even when the transistor is off, we still have this bipolar device sitting there with a certain gate action or base action, which is not as good as it would be with an ideal bipolar device, but darn close. So this is exactly what you see. And there's one thing we know about bipolar devices. The most important property that differentiates bipolar devices from MOS devices. What is that? current is exponential as a function of VBE, right? The bipolar current IC is equal to IS e to the power VBE over the terminal voltage, right? So it's an exponential relationship. And that's exactly what we see here, right? If you take a log curve and you take an exponential, it becomes a linear line. So we see this exponential roll-off of the current of our transistor below the subthreshold voltage, okay? That's very important. So the good thing is exponential, which means that if I reduce my VGS below VT, my current is going to drop quite rapidly, but it doesn't drop immediately. Obviously, if I really would like to have the best possible transistor, I would like to make this thing as steep as possible. And the steepest I can get for an ideal bipolar device would be that if I reduce the voltage, let's say with about 60 millivolts at room temperature, if I reduce 60 millivolt, that's not, well, it's a little bit more. So let's take 60 millivolt, then the current would drop with a factor of 10. That's what would happen in a bipolar device. 60 millivolt reduction in VBE reduces the collector current with a factor of 10. We call this 60 millivolt per decade. And that's an ideal bipolar transistor. Unfortunately, as you can see, this is not an ideal bipolar transistor because there's a capacitive coupling here. So we're not going to be as good. But this is the best you can do. It's a big hassle because I think there's about thousands of researchers right now all over the world trying to figure out to make a transistor where the subthreshold slope, that's what we call it, actually is less than 60 millivolt per decade. Because it would be nice, right, if I basically drop it with 60 millivolt and I can reduce the current with a factor of 100. Wouldn't that be nice? People are thinking about ways of doing that. Nothing real yet, but there's some interesting ideas out there. Okay? So that's the real problem. Because, now, why do I worry about this now, and why did I worry about this thing 10 years ago? Right? Any idea? That was always there, right? We always had that bipolar device in there. We always had that subthreshold current. Why did I worry about it? Yes?
Because the threshold used to be much higher.
You're totally right. If I basically was running at 3.3 volts or at 5 volts, I could work with thresholds of 800 millivolts. Now, 800 millivolts is a very long distance from zero, if you think about it from an exponential fashion. Nowadays, we have been shrinking the supply voltage, our thresholds have come down. As a result, if the more I move this curve to the left, the more this point is going up. Right? So my curve goes like this or like this, and as a result of that, the current at 0 VGS is increasing. And that's the real problem we're having today with those devices. So this is the same thing, just some equations. As I said, it looks like a bipolar device. The subthreshold current, ID, is equal to I0, KT over Q. KT over Q is the terminal voltage, 20 millivolt at room temperature approximately. VGS minus VT over N. And N is this factor which is, I call it the non-ideality factor. If I would have an ideal bipolar device, N would be equal to 1. However, we have this capacitive divider sitting there, this diffusion capacitance or this depletion capacitance over the oxide capacitance, which makes it less ideal. And as a result of that, we don't get 60 millivolt per decade, but we get more like 80 or 90 millivolts per decade. So it means that if I want to reduce the current with a factor of 10, I have to drop VGS with a factor of 80, 90, sometimes even 100 millivolt. So the slope is not as good as it would be in the ideal case. Instead of having something that steep, it's more like this. And that's this N factor here, which causes this. Okay? So most current day transistors will be around 90 millivolt per decade approximately, if you look at the different technologies. So this is a big problem, as I said, because it makes all our chips leak almost continuously, and people have spent a lot of thinking on how to get around that. We're not going to discuss too much in this class about this thing. This is, for those of you really excited about that stuff, 241 is spending weeks and weeks and weeks of dealing with leakage. Yes?
A question about the leakage. So the leakage is from the plastic BJT. So also the BJT at the base, the voltage is from the voltage divider of the capacitor.
That's right. So so what you have is really, you have your gate voltage. Your gate voltage couples into, you have to turn your channel on, right? If you have to have basically charge injected into to make up for the, we have to go to the whole operation of the bipolar device yet, but you really have to put in minority carriers back into the base. That's really what it is, and that's done to this capacitive divider. But a capacitive divider is not an ideal coupler. It's a division. And that dividing factor basically creates that factor. That's why we don't get 60 millivolt, but 80 or 90 millivolt per decade.
And also, it works in a DC. In a DC.
I try to understand what you mean by that.
I mean the.
Yes.
Yes, and
so
also.
For instance, I take a gate, an inverter, and I put a 1 at the input, and I leave it there. That in that case, the NMOS is going to be on, the PMOS is going to be off, but PMOS is not going to be. There's going to be continuous current flowing through that PMOS. So if it really would be very big, you would get almost a resistive divider, right? And your VOH and VOL will not be equal to VDD or 0 anymore. But in reality, the ratio is still high enough in such a way that you still can assume that your 1 is a VDD and the 0 is a 0.
So, yes, in this bipolar model, so there should be a current, a very small current from the base. So according to this model, so I'm curious about where is the current from?
The base current?
Yes.
Yeah. So that's a very good question. Where does the current? If you basically look at a bipolar device, you have to add your total current is your base current, collector current, and emitter current. So you actually have also current flowing. You have your substrates sitting there that basically flows, and can actually. So this is not completely isolated, right? So you basically have your channel, and there's current from the substrate. I think it's probably substrate current that basically flowing right into your channel. But it's a good question. It's exactly, obviously it's not going to come from the gate. And the gate basically just provides the voltage factor. Now what is going to basically compensate for the recombination of the holes and the electrons in the channel? I think it must come from the substrate. That's the only place where I could see it coming from. That's a good question. I have to think about that one for a second. Okay. So same thing, 90 millivolts. I think that's kind of. So if you lower the VT by 90 millivolts, in that case, the leakage current is reduced by a factor 10. If you reduce it by 180 millivolt, remember, it's a factor 10 per 90 millivolt. We reduce by a factor of 100x. So it's an exponential, as we obviously have pointed out. One more thing I would like to mention about the subthreshold current before we go and start talking a little bit about buffer sizing. There's another little effect. It's kind of interesting curve here. What I'm plotting here is the ID versus VDS of a transistor, MOS transistor, an NMOS device. And this looks pretty much like a normal ID versus VDS curve, right? But the only catch here in this curve is that VGS is smaller than VT. So this is a transistor that's off. So what I'm basically plotting is, as a function of VDS, I'm plotting what the drain to source current is. This is leakage current, because the transistor is off technically. Now, what you see is an interesting factor here. You see that it almost behaves like a normal transistor in on mode. So you have almost like a linear region, and then a kind of a saturation region you would expect, something like this, right? In reality, however, we see another effect happening. We see that if you increase VDS, we see actually a fairly strong increase in the leakage current. For those voltages that are, definitely if you go, let's say, beyond half a volt approximately. Very strong increase. So you have transistors off, And what it really shows now is that the leakage current that's going to flow to that off resist is really going to be a function of the voltage I'm applying between the drain and the source. If I apply a fairly large drain source voltage, we see that the leakage goes up substantially, which is not very nice, because think about it again. You have your inverter, and let's suppose that I have a 1 applied here. The NMOS is on, which means this is at 0 volt. This is at VDD. We see that the PMOS device that's off has a full VDD over it, which is the worst case condition from this perspective here. Basically, it's increasing the current quite expensively. This is called, has a special name, this effect. It's called DIBL, drain-induced barrier lowering. A long word. So just remember DIBL. Everybody calls it DIBL, the DIBL effect. And DIBL is claimed for a lot of harm in the world, sometimes too much, but it's definitely something that harms us. And I can try to explain this just in a couple of words why this is true. What's the case? It's kind of similar to a certain extent. It's not entirely correct, but think about again when you looked at channel length modulation way back. Right? Channel length modulation, remember with an MOS transistor, you see that the current of the transistor goes up in saturation mode if I increase VDS. And why was that? Because the depletion region around the drain region was expanding, and as a result of that, you kind of got a shorter channel, right? So you almost got a shortening effect in the channel. Now think about it this way. Suppose I have a transistor here, and you have a drain and a source region, and around this drain and source region we have some depletion regions. So all these little dotties here delineate a depletion region. Okay? Now what do I need to do to turn on a transistor? What determines the threshold? Well, what I have to make sure is that I can create strong inversion at the surface of my device. I have to deplete the channel first, and then I'm basically going to create strong inversion. However, now, if I have a very short device, very short channel, and I have a fairly large voltage at the drain, what that voltage at the drain is going to do is it's going to widen the depletion region around that drain region. Right? The larger I make VD, the broader the depletion region around the drain is going to come. So what I do is by applying a certain, even when the transistor is off, if I make VD larger, I'm starting to deplete part of the channel automatically. So it actually becomes somewhat easier for me to turn the transistor on because I have to do less work. Part of the channel is already depleted anyhow, so I only have to deplete a little bit of the channel and then strong inversion. Think about what that means. That basically translates in some sense in kind of a reduction of the threshold voltage. What it really says is that by increasing the drain voltage, I'm decreasing the threshold voltage. That's nasty, right? Because now the threshold voltage is a nice parameter, right? You take your SPICE deck and it says, here's your threshold voltage of your transistor. And now suddenly I'm going to tell you that the threshold voltage of your device is a function of the drain voltage. It becomes a value or a voltage dependent or a signal dependent type of voltage. It's a variable. And that's exactly what's happening here. So if you go back to this picture here, when I increase VDS, what I actually do is, if you look at this factor here, this is the equation describing this effect. I effectively reduce the effective threshold voltage of the device. And as a result of that, I'm going to get more current because my VGS minus VT is going to increase. And bingo, my current goes up exponentially. As it is. It shows clearly that this is an exponential effect. So DIBL is something that we're going to have to take into account. Definitely when you start going at 120, 90, 65 nanometers, absolutely, it's an important effect that plays. And it increases the leakage effect more than you would expect. That's why people were surprised initially. Why do we get so much leakage? And then they discovered, well, gee, it's all DIBL that basically is causing this thing. Okay, but remember that. We'll come back to that later in the semester. But the bottom line is it just changes the depletion region or the amount of depletion in the channel. It's a very simple explanation for it. So I plotted this here. This is kind of what it shows. It shows that the threshold goes down with VDS. There's one last effect I want to show you, some parasitic effect that occurs with non-ideal or subthreshold, very short channel devices. Another thing that basically impacts the threshold of a transistor is the length of the transistor. So I have a choice, right? I take my 90 nanometer transistor. What does that say? Well, I say the minimum length I can design for my channel is going to be 90 nanometers. I cannot make any channels that are smaller than that. Well, you can try, but it's at your own risk, and it probably won't work. So 90 nanometers is your minimum channel length. You can also obviously design it with longer channel length. Nobody prevents you by making a channel of 120, 150 millimeter, or whatever it is. Analog designers do this all the time. They like to do that. They make transistors with different Ws over Ls and all that kind of things. Digital designers don't. They always like to use minimum size devices, length devices, because they care about current, fast, speed, so they always like to have W over L as big as possible, so you make L small and you make W large. So most digital designers work with a minimum channel length. Now that comes with a risk, because again, it's worthwhile to do, you say, well, gee, I'm going to take my technology and I'm going to fab a number of transistors. 90 nanometer length, 120, 150, 200, and so on and so forth. And I'm going to measure the threshold of each of those devices. And what you see is the following thing. This is the effect that I show here. If you go for very long channels, threshold is kind of flat, which you would expect. No impact of channel length on threshold. There's nothing in the threshold equation where channel length pops up. It's not in there. So threshold is flat, 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 flat. And then suddenly you get around to this minimum feature size. And what we see is that the threshold starts to drop. Again, this could be explained quite intuitively. Think about it for a second. Remember what I said about the DIBL effect? Think now about what would cause the threshold to drop when I make my channel length very small. Any idea? Any thoughts? Very similar thought process as what I did. Think about it. Yes?
The depletion region now represents a larger portion.
That's exactly right. If I make my channel very, very tiny, the depletion regions of the source and the drain connector are taking a larger fraction. So a larger fraction of the channel is already going to be depleted. It's easier to turn the transistor on. Your threshold is lower. Okay? Now that's kind of a pity, because suppose now I design at 90 nanometers and say, okay, here's where I'm sitting. That's okay. I get a fairly decent threshold. Leakage should be fine. So this is 90 nanometers. So he said, well, gee, I'm not worried at all because my threshold seems pretty good. You go to your friends in the fab, and they fab, and all your chips come back. And you say, my goodness, what did they do? My leakage seemed to be way higher than expected. Remember, the channel length that you design is a nominal value. It's a target. They're going to try real hard to make sure that your channel lengths are the same thing, but they're not always going to be right. Sometimes the whole process could be shifted up a little bit, and instead of having 90 nanometers, everything ends up at 75 nanometers or 80 nanometers. And as you can imagine, a linear drop in threshold voltage means an exponential increase in leakage voltage currents. So suddenly your chip can leak quite a bit more. So this is something that is, I've seen it happen, so don't worry about it. I've seen chips coming back and said, my goodness, what is going on? And we start figuring out, and yeah, all our channels were about 20 nanometers shorter than they were expected to be. So process variations basically make this thing a very dangerous proposition. You're sitting there at the edge of the sword, and it can cut both ways. So you can get better, or you can get a lot worse. So what, fortunately, our friends in the fab are our friends most of the time. They have found some tricks around this. So they said, well, what we're going to do is we're going to make life a little bit better, safer for you. So they do some extra implants. They call it halo implants, which kind of increase the threshold a little bit around this 90 nanometer edge. And then it drops off real fast. So it gives you a better safety zone. However, if they really mess up, it gets bad, real bad, because suddenly you fall off a cliff. But this halo implant is something that most technologies do these days, and kind of getting around some of that channel length effect. But remember, thresholds is not this kind of fixed thing. It is a function of this drain source voltage, it's a function of the channel length, and it's going to be a variable thing. Every chip will have different thresholds on different transistors because of doping variations and all that kind of stuff. Okay? All right. Clear? So that's kind of my first introduction to leakage. We'll come back to that later, but I'll keep it to that for the time being. Any other questions on this? Good. Let's talk a little bit about sizing of an inverter chain. So let's start to do some design. Okay. Now, I think this is the first part of the class that's really going to start to be fun, because now here's creativity going to start to bubble up. Here's my problem. I give you a problem, or say somewhere I have a chip, and I have to drive a large capacitance. Right? Somewhere you might have to go off chip through a pin, and I say, well, gee, I have a capacitance there that's 10 picofarad or something like that, and I would like to drive that capacitor as fast as possible. I want to make sure that I can charge it up and charge it down as fast as I can for performance perspective. So the question is how to do that, right? Well, so there's a number of ways to do that, and we'll come back to some of those. But let's assume, say, that the way I'm going to do this is by creating a chain of inverters. And it's going to be very clear in a minute why I want to get a chain of inverters and not a single one. So I'm going to get a chain of inverters. So I have somewhere an input here. That's my input on chip. Comes out of my logic, comes out of an ALU. This could be my bus, for instance, and this is the ALU. The ALU is real fast, clocking like crazy, and then you have to bring the signal on the bus, which is a large capacitor thing going all over the chip. So I'm going to try to put some circuitry in between in such a way that I make this bus move as fast as I can. So as I said, we're going to use an inverter chain for that. But then the first question you ask yourself is, how many inverters? 1, 5, 1,000? How big should I make them? Should I make them all the same? Should I make one larger than the other one? These are good questions to ask yourself. And the beauty of it, this problem is it's one of the nicest problems. It's really solvable. I can actually find the optimal solution, which is not always the case in the engineering. In this case, I can tell you, hey, this is the way you should do it. This is the best possible solution. So let's start to the naive approach. So I want to drive a capacitor really, really, really fast. How would you do it? What's the first guess you would take? Remember what we said about propagation delay. You want to make something fast, TP is equal to CL VDD over 2 over I average. All right? CL is given. I have a load capacitance. VDD over 2, typically a given factor 2. Let's not argue about, yeah, you can reduce the supply voltage and things like that. No, let's not go there. So I have only one parameter to play around with. It's I average. So that basically predicates right away for me a solution. If I say, okay, I'm very clever, I know how to make this thing, I can make it as fast as I can, and I know exactly how fast I can get it, well, obviously I would like to make I average as big as possible. So what I'm going to do is that's the macho approach. I say I'm going to make one really, really, really big inverter. I make it as big as I can. I make giant transistors, millimeters long in terms of width and so on and so forth. So that's approach number one, and sure enough, it's going to give you the best solution. This is the fastest possible way. It's a very big inverter. And you make it this big that at that point in time, remember, the delay of an inverter has two components: intrinsic capacitance, load capacitance. So if I make my inverter bigger and bigger and bigger, the load capacitance is fixed. Right? That's an external. But I'm increasing the intrinsic capacitance. So if I make my inverter as big till a certain point that the intrinsic capacitance becomes the dominant factor, at that point in time my delay will basically flatten out, and that's the optimum delay I can get. I cannot go any faster than that. Right? So that seems to be that, hey, we're done. Right? Why spend any more time on this thing? We're finished. Well, that's like, it's kind of like taking a problem and you divide it up in pieces and say, I solve my problem and then let somebody else solve the other problem. That's exactly what this thing does. Because now, I've designed this really, really, really big inverter, but the problem with the big, big, big inverter is that it has a big, big, big input capacitance as well. So you shift the problem to the previous gate and say, you solve the problem, not me. And then you can do, say I'm going to put another big, 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 big inverter there. You shift it again to the one previously. So that's not something you can do. So this is a solution that kind of works, but it's kind of is passing the buck to somewhere else. So it gives the right solution. Yeah, obviously it's clear that if I want to have a big capacitor in the end, I'm probably going to have some big transistors way in the end. Right? That's a good idea because I need to charge that capacitor. I need a lot of current. Obviously, I'm going to have some big transistors there. But then it's not sufficient because obviously these big transistors need to be driven themselves as well. And that's where this chain of inverter idea comes from. What you do is, well, say we're not going to take one inverter, but I'm going to have a chain of them. I'm going to make them gradually bigger. I'm going to size them up step by step in such a way that everything is nicely balanced. Question is, what is nicely balanced? What is the right ratio? That's what we really would like to figure out. Okay, so as I said, this is fun because it's finally engineering. We have an optimization problem here. We have a set of constraints. For instance, the constraint that's very useful says, well, the input capacitance that I can see to that whole logic circuit should be of a certain maximum size. Like for instance, if I have an ALU that has to run at 5 gigahertz, I cannot afford to load that ALU with 2 picofarad. So the only load I can see maybe there might be in the order of 10 to 20 femtofarad. So I define the input capacitance. I constrain the load capacitance on the input that the input sees. So you have your block here. You have your big capacitance. I want to make sure that the capacitance that I see when I look into this block is tiny and doesn't load the ALU or whatever that sits in front of it too much. So we start with a given minimum input capacitance. It could be a minimum inverter size or something like that. We have a given output capacitance, and then we're free game to design all the stuff in between that. So that's really what we do. We constrain the size of the first inverter. Okay? Okay. So, good. So now you kind of can imagine that there is an idea of having the sizing up of inverters, right? You start with this tiny one that has the fixed input capacitance. You size it, then you use that one to drive the next one, and you gradually make them larger till the last one can drive the big output capacitance. Okay? So, 2 questions. How many inverters? Number 2, how do we size the inverters? How do we size them up? So I'm going to make life easy, and I'm going to divide it into 2 problems. I'm not going to solve it all in one shot. Let's make it easy a little bit. First, assume that I know the number of inverters. Let's say you might use 3 or 5 inverters. Okay? So I'm going to fix the number of inverters. Later on, we're going to remove that. And what we're going to try to, and we are given the size of the first inverter, obviously, and we know the load capacitance. So our goal is to minimize the delay of the overall inverter chain by picking the sizes of those fixed number of inverters. Okay? So that's what we're going to do. And as you will see, it's a very nice, beautiful analytical problem. It's easy to solve. Before we go there, I'm going to make some simplifying modeling. Well, we know our propagation delay. I'm going to make some assumptions. Symmetrical design. So I'm going to assume that PMOS and NMOS have the same driving force. Make life easy. So that TPHL, TPLH are going to be the same. For that, we assume that we take the PMOS 2 times larger than the NMOS, like we typically do. Okay? So symmetrical design. we're going to analyze this in RC network. So the propagation delay is going to be ln2 times RNCL for the H to L, from the high to low. And for the low to high is the resistance of the PMOS times that, but they're the same. And the load factor on the previous gate, the input capacitance here is going to be 3 times W. W is the size. We size both PMOS and NMOS in the same way. So if you're going to make an inverter bigger, remember the PMOS is 2 times larger than the NMOS. If I want to make an inverter with more driving power, I'm going to multiply both PMOS and NMOS with the same factor, which we call W. Okay? So our overall input capacitance is going to be 3 CG, which is your minimum size, input capacitance times W. But the wider I make, the more load capacitance, input gate capacitance I will get. So we have all those parameters here. So we can find out the propagation delay of this gate quite easily. So you have your load. This is a typical inverter. I'm just going to go, this is just repeating what we did before. It's nothing new, but I'm just going to reformulate a little bit in such a way that I'm going to come up with a very simple equation that I can then use over and over again. Simplify life a bit. So if you look at this inverter here, as I said, symmetrical, PMOS, NMOS, we know the input gate capacitance, that's 3W times CG. The output load capacitance, I assume right now that we just take the diffusion cap, CD. Let's ignore the gate drain overlap capacitance, which is small compared to the diffusion cap. So we have a capacitance here, which is the intrinsic capacitance, which is going to be equal to 3W times CD. Remember, when I size up my inverter, I increase both the diffusion capacitors as well as the gate capacitor in the same ratio approximately. Okay? And my resistance is going to be equal to proportional to L over W. So my propagation delay is going to be the resistance times the total capacitance. Total capacitance consisting of the intrinsic capacitance and the load capacitance. Okay? And K is the sizing factor here. K is basically the factor that basically take into account well, this K is a constant factor, which is ln2. Okay? So that's my typical delay equation if I would write it all out. It says it's K times R squared times L over W, 3 times WCD plus K times R squared times the load capacitance. Okay? Nothing extraordinary here. This is exactly the same thing as before. But now I'm going to rewrite this a bit. Because what we see here is that if I look at the delay now and I plot it, you see that we get 2 factors in our delay. There's a delay, basically it's a linear factor. If you change the load, CL, you see that the delay goes up linearly with CL, as we expected. Right? So if CL would be 0, the only delay we're going to get is that intrinsic delay of our inverter, caused by the diffusion capacitances of the transistors. So we call this the intrinsic delay of the inverter. And then you have a second factor, which is a function of the fan out. Okay? And it's a linear factor of the CL. So the delay goes up linearly with the load capacitance. Okay? I'm going to take it all together, and I come up with this very simple equation. This is the crux of what I analyzed this whole thing here. It says my propagation delay of an inverter is equal to this simple equation. It's T inverter times gamma plus F. As simple as it can be. Now, let me explain some of the parameters. You can basically go to the analysis and things like that and come up with it yourself and all this type of thing. Gamma is actually the ratio between, let's see, it's somewhere up here, is equal to C int over C in. What is C int? Remember, C int is the intrinsic load capacitance of the inverter. That's my diffusion capacitance. C in is the gate capacitance of that same inverter. So what gamma is the ratio between diffusion capacitance and gate capacitance of an inverter. I design an inverter, and I measure the diffusion capacitor at the output, and I look at the gate capacitance at the input, and I take the ratio of the two. That's my gamma factor. Now, interestingly enough, for most of the technologies we're typically playing around with, those things are approximately the same. They're the order of 1 to 1.5, approximately. They're pretty similar in value. But it's kind of, what it allows me to do is refer intrinsic capacitance back to the input in terms of load capacitance for the previous gate. So that's an interesting factor. So this is the gamma. So we see that then the second factor, F is what we call the electrical fan out. It's the ratio of the gate capacitance, the C-in of my inverter, to the load capacitance. So you have this inverter. We have a load capacitance CL, and we have a capacitance C-in, which is the gate capacitance. So you see that this inverter kind of acts almost like an impedance transformer. You have a big load capacitance CL at the output. You have a C-in at the input. The ratio between those two we call the electrical fan out. It's go from a capacitance C-in to a very large capacitance CL at the output. This factor F. And remember, if you make F larger and larger and larger, my propagation delay should go up what? Linearly, right? As we just showed at that curve. And that's really what this thing shows. It shows that if you have no fan out, if the fan out is 0, just intrinsic load, your propagation delay is going to be gamma times T invert. And then you start adding load capacitance to it, we get a factor F times T invert that basically increases this. Now there's one more interesting thing that I'm going to mention before we quit, and that's this last thing here. If I look at T invert, the expression, again, I take all the parameters, I model it all together and put it together in one parameter. What you see is this T invert is 3 times ln2 times the length of the transistor times the equivalent resistance of our transistor process times the gate capacitance. What we see is that in this thing, this T invert has nowhere a size factor. And W is not in there at all. It actually is independent of the size of the inverter. T invert we call the intrinsic delay of an inverter. It's a function, if now I take a big inverter or a very tiny inverter in the same technology and the same layout. Obviously, when I mess around with the layout, I can mess things up a little bit. But say you take the same type of shape topology, T inverter will be exactly the same. This is a technology parameter, not a design parameter. And it's not something you can change. It's a given factor. First thing you do, you take your technology, you simulate the thing out, you get T invert out of there, bingo, we're done. So that's the interesting thing. Is now that I have a very simple equation to express the propagation delay of an inverter as a function of its fan out, the ratio of the load capacitance over the input capacitance. Right? That's F. You have the input capacitance of the gate, the load capacitance of the gate. And that's where the sizing will come in, as we will show you in the next lecture. This equation is very important because it's so simple, it's so beautiful. I can now start combining those things and build more and more complex logic networks and actually come up with analytical solutions because of the fact that I ended up with this very simple equation. Okay? So we'll talk more about that in next lecture, which is going to be Tuesday again. So there's another lecture Tuesday, there's one on Wednesday, there's none on Friday.
Signal. I mean, is it really a DC signal, considering it's been switched around all the time?
It is. Well, it's steady state, right? The leakage is a steady state factor.
Even if it's just a straight voltage on it, it's still
Exactly. There's only So this is DC, absolutely. So that's the real problem. If it would be AC, it would go away, right? But DC is, as I said, I don't do anything, and I'm consuming current.